So today we're going to be talking about function operations. We have been looking at the graphs of functions up until this point. So now we're going to start looking at some other types of operations that we have with them. So we have our main four operations: addition, subtraction, multiplication, and division, just like with our normal numbers. And they work pretty similarly to things that we've seen in the past. So if I want to add or find the sum of two functions, I can just add them separately. Same thing goes for subtraction, multiplication, and division. The only thing we have to worry about is with our division, we need to make sure that our denominator does not equal 0. So this says, given f of x equals 2x plus 1 and g of x equals x squared plus 2x minus 1, find f plus g of x, then evaluate the sum when x is 3. So I have f plus g of x. And using the information that we had on the previous page, we know that we can separate those out by addition. And the reason we want to do that is because we know both what f and g are. So if we can get them to be separated, we can plug in the two functions that we know. And from there, we're just going to combine our like terms. So we have x squared plus 4x, and then our 1 and our negative 1 add to 0. Next, they ask us to evaluate the sum when we have x is 3. And there are two different ways that we could do this. First, we could plug in 3 to f, plug in 3 to g, and then just add those together. However, since we have already found our f plus g, we can also just go ahead and plug into that expression instead. So we end up with 9 plus 12, which gives us 21. All right, so next up, it's asking us to do something very similar. I have f plus g and f minus g. Using our properties that we had on the previous page, we know that we can rewrite this as f of x plus g of x and f of x minus g of x. So then plugging in what we know f and g are, we're going to combine our like terms again. So we get x squared plus 2x minus 3. And on our second one, we're subtracting. So we have x squared minus 4. This time we're subtracting g of x. So we do need to be careful with that because a lot of people will make the mistake of just putting the negative with the 2x and not distributing it to the 1 as well. And then notice that they ask us to indicate any restrictions in the domain or range. We're going to go ahead and just focus on the restrictions of the domain. If we wanted to find the restrictions on the range, we would just go about that by graphing our things and looking at our range that way. So in this case, we really just want to talk about restrictions on our domain. So hopefully we recall that both x squared minus 4 and 2x plus 1 are both polynomials. So remember, polynomials is anything with a positive integer exponent, and that's what those have. And then also all of my answers are also polynomials. So that means that we're going to have no domain restrictions. Anytime that we start and end with a polynomial, we will not have domain restrictions because we're allowed to plug in whatever we want into a polynomial. On our next one, they want us to multiply. So we have f times g of x. Again, we can separate this out into f of x times g of x. This is going to equal x squared times x minus 3. And since we have a monomial times a binomial, we can just distribute that x squared. And like our previous example, they now want us to evaluate at 4. And again, we could do this two different ways. We could plug into f, plug into g, and then multiply them together. Or since we've already found what f times g is, we can just plug 4 into that. So we get 64 minus, there we go, 64 minus 3 times 8, which gives us 64 minus, come on, it's not willing to work. One moment. All right. There we go. So 4 squared gives us 16. So then 3 times 16 gives us 48. And then 64 minus 48 gives us 16. And so that would be our final. All right, so next up they want us to divide. They want us to do f divided by g and g divided by f. And they're going to be very similar as we evaluate. Then the big thing is going to be that they're wanting us to find our domain restriction. And that's going to be the part that we're going to have to spend a little bit more time on because our functions are a little bit more complicated this time. I have a fraction, and then we also have a square root, which is fine. Just our process is going to be a little bit different. So because I have a square root for both of those, I'm going to go ahead and rewrite those as just one radical. And the same would be true if we had g divided by f. Our fraction is just going to be flipped. Now, if for some reason our fraction had any common factors, we would want to reduce those. In this case, it doesn't, so whenever we combine to be one radical, that is our answer. The only thing we need to worry about now is that second part, which are the restrictions. So whenever we're creating restrictions, we need to take into account that we're combining both f and g into one function, whether that be addition, subtraction, multiplication, or division. So any restrictions that we had to begin with for f or g are still going to be there when we combine them. So we need to decide what our domains are for both f and g separately first, and then we can try and combine them together. So for our f of x, notice that our x value is going to have to be greater than 0 since we have a radical. Now, we also have a radical with our g of x function. However, notice that we have a squared underneath our radical. So that's going to make this problem a little bit different now. So remember that whatever is underneath our radical has to be greater than or equal to 0. Now, a lot of our first instincts is just to add x squared, take the square root, and we will get x is less than or equal to. But the problem that we run into is when we take the square root, we get both a positive and a negative 4, which does not work in an inequality. So what we want to do to kind of get around that is we are going to solve a nonlinear inequality. So nonlinear because we have a degree of 2, and an inequality because it's not an equal to sign. We should have seen this in Algebra 2. However, I know our year got cut short, so some of us might not have. So I'm going to walk us through these steps like none of us have seen this before. So our first step when we're solving a nonlinear inequality is we want to find our critical points. And these critical points are going to be what we get by just setting it equal to whatever's on the other side. And then we're just going to solve it like we normally would. So we will add x squared over, then take the square root. So we get that x is plus or minus 2. So that would be our answer if we had just started with the equation. And these also happen to be the critical points for our inequality. Now, what we want to do from there is we're going to go back old school, and we're going to create a number line. And we're going to take any of those critical points that we got, whether that be 1, 2, 4, whatever number of critical points, and we're going to place them on our number line. And notice in this case that we have created 3 separate sections. And what we need to do is pick a number inside each one of those sections. We can't pick a critical point, but we do need to pick something in the other sections. So notice that my first section is everything that is smaller than or less than -2. So I'm going to pick -3. Then my next section is everything that's in between -2 and 2, so I pick 0. And then our last section is everything that's bigger than 2, so I pick 3. You could have easily picked any other number. However, I will say make your life easy. Don't pick something like 1.9. That's going to be hard to evaluate. Go with things that are going to be nice, give you whole numbers, things like that. So then once we've picked our values, we're going to plug those back into our original inequality. So notice that when I plug this in, -3 squared gives me 9. 4 minus 9 gives me -5. So I get that -5 is greater than or equal to 0. So hopefully we notice that this is an untrue statement. So we know that we're not going to include that portion of our number line in our final answer. So next up, we're going to plug in 0 and evaluate. Notice that we get 4, which is a true statement. And then lastly, we would plug in 3, and that's actually going to give us the same thing that we got when we plugged in -3. So notice that again, we get an untrue statement. So we know that we want to include only the portion of our graph that makes our inequality true. So it's going to be this middle section right here. And then all we need to do is decide if we want to have open or closed circles at our critical points. And the way we decide that is by going back and looking at my original inequality and saying, okay, I had an equal to bar, so that means that they can equal these 2 points. So I want closed circles. If I did not have the equal to bar, then we would have open circles. So lastly, we can kind of combine all of that, and now we can say that the domain for G has to be in between -2 and 2. Now remember that that's not our final step. We still have to go one step further. Remember that we're now trying to combine our domains for F and G into one domain. So notice we can kind of think of it like we were our other inequality. I'm going to go ahead and write out a number line because I think it makes it easier to see. So I'm looking at my 3 values that we have, so -2, 0, and 2. So notice that for my first function, we are greater than 0. So I start at 0 and I go to the right. For our second function, we have to be in between -2 and 2. And so for our new function, where we combine those 2 things, we have to pick a domain that makes both of those things true, or basically the portion in which they overlap. So notice that they're going to overlap from 0 to 2. So that means that the domain for F divided by G of X is going to be from 0 to 2. The only thing that we have to worry about, though, is remember that we have a fraction. So we know that whatever makes this denominator 0 cannot be included in our domain. So if we go back, we've actually already solved for that when we came over here to find our critical numbers. We solved and we got that x equals plus or minus 2 is what's going to make that 4 minus x squared 0. Well, -2 is already not included in my domain. However, 2 is included right now in our domain, and we want to make sure that we don't include it. So we're actually going to put parentheses around that instead. And then 0 is going to get the hard bracket because it can be included. It doesn't cause issues. Now, the process for doing our G divided by F is going to be very similar. I would still be looking at this same little number line. I'm still going to be looking at between 0 to 2. The only difference is because we've switched what's on top and what's on bottom, Now I need to make sure that I don't include the number that's going to make x 0. And that will be 0. So 0 is going to get the parentheses this time, and 2 is going to get the hard bracket. Now realize that this is probably one of the most complicated types of problems that we would see. When I ask you to find restrictions on our domain, your problem would not look like this. It would probably either be a radical or an x squared. I wouldn't ask you to combine both of them. So that's why I wanted to do this one together, because this is a more complicated example. If we do it together, then we should be able to handle any of the other easier examples by ourselves. So let's look at one more example. They give us f of x equals x squared plus 7x plus 12, and g of x equals 3x minus 4. So again, like with our previous examples, we can separate this out by multiplication. And we have f of x, which is x squared plus 7x plus 12, and g of x, which is 3x minus 4. Now, with our last one, we were able to distribute because we had a monomial times a binomial. In this case, we have a trinomial times a binomial. So we're actually going to have to do what I like to call the rainbow method, because we have to multiply everything in our first parentheses by everything in our second parentheses. So it kind of creates those rainbow arcs. So our first thing, we're going to do x squared times 3x, which is going to give us 3x to the third. Then we're going to have x squared times negative 4 gives us negative 4x squared. Continuing on, 7x times 3x gives us a positive 21x squared. 7x times negative 4 gives us negative 28x. 12 times 3x gives us a positive 36x. And then negative 4 times 12 gives us a negative 48. So then combining all of my like terms, we have a negative 4x squared plus 21. And so combining those, that gives us a positive 17x squared. And our next one, we have 36 minus 28x. So we get a positive 8x. And then our 48 stays the same. So again, I really only care about our restrictions on our domain, and because we started and ended with polynomials, we're not going to have any restrictions in that case. All right, so now going on, we have f of x divided by g of x. So again, I'm going to separate those out. I'm going to plug in my f of x, plug in my g of x. And we do want to try and simplify as much as possible. So notice that our numerator is going to factor to x plus 3 times x plus 4, because we need to make sure that we don't have any factors that reduce. And in this case, we don't. So that would be our answer, except for we do have to worry about that domain restriction. This one's going to be a lot easier. So remember that whatever's in our denominator cannot equal 0. So I would add 4 and then divide by 3. So that would be my domain restriction. And this would be much more similar to something that I would ask you in your homework or on a test. So as long as we can do something like this, we're okay.